So now we're going to talk about a very important topic, buckling. So when a material is put under compression, it's typically not going to fail via crack propagation. Instead, it's going to fail via buckling. So we're going to focus on column buckling, and we're going to define a column as a basically slender rod, and buckling is an instability phenomenon. So when we say stability, stable systems will return to the initial state. Unstable systems will basically the ball roll down to the heel. So let's start off with first an ideal column with pinned ends. So we are going to assume we're working with a straight beam, linear elastic material, load that's aligned along the column axis, really along the longitudinal, the long axis of that column. When we have, there's several states here. So first, you elastically shorten, but at some critical point, the beam becomes unstable. It will start to bend and curve, and we want to figure out, based on the material and the geometry of the beam, when will this happen? When will the material fail via buckling? So one of the ways that we can do it is drawing a free body diagram. Again, same type of idea, constitutive equations. So initially we shorten it. Once it reaches its critical stability or instability, it will be unstable, it buckles, and we can develop an equation that relates that curvature and that resultant moment to that buckling phenomenon. So we would solve this second order ODE. We know that basically there's no deflection at zero, the pinned ends. And the only non-trivial solution, we know that C2 will be equal to 0 when we solve this ODE. We know that C1, it could also be 0, but the non-trivial solution will be when that sign becomes 0. So when the square root of P, the load, length over EI is equal to some integer n pi value. So our critical load will be defined as such. So it's very interesting. It makes sense, right? The longer the column, the lower the critical load. The stiffer the beam, the higher the critical load to buckle. The higher the moment of inertia, the higher the critical load. So you see here that L squared phenomenon, length has a critical scaling that goes on here. So one phenomenon you might think and may want to do, I have my phone is ringing here, but my moment of inertia, you may think that may be the scenario to reduce that buckling. But instead, when you have hollow materials, you can get this phenomenon called local buckling and basically kinking. And the same phenomenon actually happens with open cell foams as well. So open cell foams can be treated, and you can look at the compression of cellular materials and open cell foams similar to a buckling phenomenon as well. So if you ever take a cellular materials class, you can look at essentially the relative densities and see how that scales as well. Typically, you'll get some densification. But anyways, before we get into plasticity, we need to cover torsion.